Hello everyone, this is my Physics Lab 5. The purpose of this lab was to observe and analyze a spring mass system and to write code to model the system and compare the predicted to the observed motion. The results I got was that total energy remained zero to uphold the energy principle, and the model generally followed these experimental values. We'll get into that a little bit later. So here are the key concepts. Obviously, we have Newton's second law to propagate that motion, right? We can also see this as force equals mass times acceleration. The spring force, right, which is, as you can see, negative k times the magnitude of L minus the relaxed length times L hat, which is your direction vector. Period of oscillation, we use this. This isn't really directly used. This is more to find k, even though k is given to us. With the energy principle, right, the main one that we use here is this delta E is equal to 0, right? One is the energy summed up equal to 0, but we also want to see the change in energy if there's no work being done on the system, right, should equal 0. And since everything is a system, which we'll get to, we don't want any work. We'll also be using these three, the K, the use of G, and the use of S equations, because those are the types of energy that are in the system. Initial conditions, right? This was given from the video linked in the lab instructions. So this was just copied. The ball position was taken from my own tracker, and the ball velocity was also taken from my own, calculated from the positions, the first few positions in my tracker data. Okay, so here were the calculations, right? Where we have the gravity, right, is just mass times 9.8. The spring force, right, is just negative k times s, where s was calculated, and you can see s being calculated right here, right? We'll get to that a little bit later, but the F net is just those two forces, right? Well, those are the only forces acting on the system. We use the momentum principle, Newton's second law, to update velocity and position. And now we get to L, right? The calculation of L is just the relative position of the ball with respect to the spring, right? So we just subtract ball dot pos minus spring dot pos. And to get S, right, we just use, basically it's just a difference between L and the relaxed length, so we use the magnitude of L, and we give it direction using L hat. The energy equations were from the equation slide that I showed, the key concept slide. This is just a code version of that, and the deltas are just with respect to the initial, relative to the initial version of those energies. All right, so here's my observed data from tracker. You can kind of see this elliptical motion of this weight. You can see the x and the y. So yeah, here's the model data. So this is the from the model. You can really see how the energies kind of cancel out to make it zero with the sort of sinusoidal motions, and yeah. The reason they're going up and down is because, again, this is some sort of periodic motion. As it sort of gets closer, as the spring gets more coiled, right, your velocity goes down, meaning k sort of decreases. You kind of see that. So yeah, comparison, right? Overall, the general trend is there, right? There's a periodic motion. That period looks very similar. There's a little bit of a shift because of how the observed data is just sort of presented in the code, how it's put in there. But other than that, the x is very similar. Even the amplitudes are similar, right? The y direction, the amplitude for the experimental data is smaller than the amplitude for the model data, right? And this may be due to some error in the tracker, or maybe the constant values, maybe k should be less stiff. Maybe the velocity was not sort of in the negative direction enough, right? And that's where I get to here, right? Maybe this inaccurate tracking, which results in inaccurate starting velocity. Maybe there's the inaccuracies in those initial measurements. And then questions, right? The energy principle is satisfied, as I mentioned, because delta E is always 0. The energies cancel out, total energy is 0. And the two estimates, right, for x and y when we talk about the period differ by around 0.01 seconds. So pretty similar, right? The reason that they might differ is because different forces act in the x and y direction, right? When you talk about the spring force, because it's at an angle, right, the rate of change that the force enacts on this velocity in the x and y direction, right, might be different because the magnitudes may change at different rates or are different, due to that angle of the spring force. That rebounding force is different. So yeah, that is lab 4.